Hi everyone, thank you for watching this video. Today I'm going to talk about attribute efficient learning of half-spaces with malicious noise. This is a joint work with Chicheng at the University of Arizona. So an half-space U is such that for any instance x, the label y is predicted as sine of u times x. So our goal is to collect n number of labeled data x1, y1 through n, so we can approximately estimate u. So if we know that if there's no noise, then we can apply perceptron or linear programming to estimate u. And the sample size is polynomial in the dimension d. So in this paper, we will consider attribute efficient learning, which means if the target half space just depends on a small set of features, for example, it depends on 3 features, then we would hope that the sample size can be reduced to polynomial in S and the log of d. And this is essentially possible. We just need to add L1 norm constraint to SVM. But again, the condition is that the data is noise-free. So one natural question is, what will happen if both features and the labels are corrupted? And in this talk, we will concentrate around the malicious noise. Okay, so this is a malicious noise model. We have a learner and an adversary. So each time the learner requests a sample, the adversary flips a coin, and with probability 1 minus eta, it generates clean data. And with probability eta, it can generate an arbitrary pair of x and y. So arbitrary here means it may inspect the learning algorithm. So this could be very dangerous for us. Okay. So we started this problem on the empirical learning model. So in this model, there is an underlying distribution D, which is unknown. And there is also an unknown half-space U, which is supposed to be S-sparse. We have RID samples XY from the malicious adversary. And our goal is to estimate U with sample size polynomial in S and the log of D. So in addition, we will consider the challenge of acquiring labeled data. This is motivated by many practical applications where unlabeled data are often cheap, but labeling is very expensive. So we will also do active learning, where initially we just have access to unlabeled data, x1 through n, but we can make interactive label queries to access y. So the hope is that we will still able to estimate u with few label queries. Okay, so this is our main result. We show that it's possible to pack-learn the underlying half-space U with in polynomial time if the underlying distribution D is isotropic log-concave, and if U is S-sparse, and the malicious noise level eta is omega of epsilon. So here epsilon is the target error rate. And we know that such sort of noise tolerance is near optimal. So we compare with previous works. So if we apply the work of adversary, Balkan, and Lom, they just give sample size and the label complexity quadratic in the dimension D. And if we combine this work with Zhang, then we can improve the label complexity, but we still have a quadratic dependence of D for sample size. So in this work, we showed that the label complexity is linear in the sparsity and the polylog in D. And also we showed that the sample size is quadratic in S and the polylog in D. So we know that our label complexity is near optimal, and also the sample complexity is attribute efficient. So this is our framework. We will use localized sampling plus soft outlier removal, which was proposed by adversary Balkan and Long. So here is the main insight. They basically show that if we can choose a local instance space and also a local concept space. And if we are able to show that the empirical hinge loss of clean data is a constant in such localized space, then the overall error rate will be very small. So what do? We just need to approximate the hinge loss of the clean data in the localized region. But the main challenge is, of course, we have no idea which of them are clean and which of them are dirty. So we will need a very important attribute efficient outlier removal procedure to identify the clean data. Okay. So let me talk about localized sampling first. So just suppose these are the unlabeled data, and this is the ground truth U. And we have a current iterate WT-1. So we will construct a band B. And we will sample the points within B. So this is because points within the band B have high uncertainty in terms for the current iterate WT-1. So if we concentrate on these points, then we are able to reduce labeling cost. And more importantly, this limits the power of the adversary. So just imagine that we don't sample from B, we sample from the whole region. And just suppose this is the outlier returned by adversary. So what's going to happen is that we will try to fit the data. And to do so, we will have the new iterate WT, which is far away from you. And the bandwidth BT shrinks over phases geometrically. So this is because as the algorithm proceeds, we will be more confident about our estimate. Then let me talk about the localized concept space. So this is an intersection of a two number and a one number. So the two number is kind of standard in active learning. It serves as a trust region. And so if this is our current iterate, then the two number will be the green bar. And the hope is that if we pick the radius in a proper way, then the ground truth lies in the green bar. So that also indicates we will find a new iterate within this bar. And of course, we will consider attribute efficiency. So that is why we also add a one norm constraint. So before talking about outlier removal, I will talk about two different types of outliers. The first one is weak outliers. So just suppose this is a point. This is the arbitrary point returned by adversary. So, and also suppose it's labeled as negative. So what's going to happen is that, again, we fit the data. So we slightly update our model from WT-1 to WT. Okay. So this is called weak outliers because we are not really far from the ground truth. Then let's think about the strong outlier. So what is strong outlier? So consider this point, and it's negative. So we fit the data, and we have the new iterate WT. So we can see that it is far from the ground truth view. So this kind of data will be called strong outliers. So here is the intuition for outlier removal. So once the adversary must generate the clean data, so basically we can imagine that distribution D is, for example, the uniform distribution, then we will have uniform data over the region, over the band. But once he has the power to find or generate arbitrary pairs of X and Y, then he must concentrate on the strong outliers to fool the learner. So that is, so these are the points generated by the adversary if he wants to fail our algorithm. Okay. However, such outliers can be detected. So this follows the intuition that if this is our data, then there must be a direction with large variance. So what we do is we try to find a weight for each point such that the related variance is small on all the directions. So this is our attribute-efficient soft outlier removal procedure. We have unlabeled data x1 through n, and we try to find weights q1 through n for each point. So each qi is between 0 and 1, and we hope that the related variance will be as small as b squared plus r squared. So basically, this follows from our analysis that for clean data, they have such kind of variance bound. And of course, we cannot push all the qi to 0. Otherwise, there's no information from qi. And so here we will suppose psi is empirical noise rate, So basically, you can think about in this way. We have 1 minus psi times n number of clean data, and qi is the indicator function of clean data. So the sum of qi is supposed to be greater than 1 minus psi times n. So it remains to show that we can verify all these conditions, especially for the second condition. So we need some very efficient verification procedure. So let's take a closer look at it. So the objective function is we try to maximize a quadratic function, and we have a convex constraint. So the constraint is fine, but overall this problem is non-convex and it's closely related to sparse PCA. And we know that computationally it is hard. Okay. So what we do is we try convex relaxation. So we will consider a natural convex relaxation. So we consider an upper bound of the quadratic function, and we introduce a new variable h. So this h is a positive semi-definite matrix. And if we look at the right-hand side, it is a linear function in terms of h. Okay, and then we relax the two norm constraint into Euclidean norm constraint, and relax the one norm constraint to the matrix one norm constraint. So in this way, we can find that in order to upper bound the quadratic function, we just need upper bound the linear function, and this is a convex problem. Thank you.